All right. Hi, Stat 113 people. So for this week, we're going to finish up our simple linear regression. And so we've kind of already talked about the basics, like the basic model, some of the interpretations, the assumptions that we have to make, and now we're going to move into inference for today. And so inference again just means like we're going to do a hypothesis test and we're also going to do a confidence interval. And so we're sticking with our same example just to have some kind of continuity. And so remember we were looking at this model with course evaluation score as the response and attractiveness of the professor as a predictor. And so, one question that we might be interested in answering is whether the attractiveness rating is associated with the course evaluation rating. And so, I think as kind of humans, we would kind of hope that that's not true, but we could kind of see how there could be some biasness there and that these two variables could end up being associated. And so the corresponding hypothesis test is just a test on whether the slope coefficient is equal to 0. And so let's take a second to draw a picture of why that would be the corresponding hypothesis test. So I'm just going to draw a little graph with attractiveness on the x-axis, course score on the y-axis. And so if there's no association between these two, then that would indicate just a straight line going across, meaning that the slope of that line would be equal to 0. And so why does that mean no association? Well, you could think about it a couple ways, but the way that I kind of think about it is that if we were to predict course score from like a low value of attractiveness, that's going to be the same exact prediction for a high value of attractiveness. So it doesn't really matter. We're predicting the same score no matter what attractiveness level we're at, meaning that the two are not associated. So that just means that we're predicting the same score no matter what level of or what value of attractiveness. So that's why the slope equals 0 is going to mean that there's no association. Okay, so if we're good with that, then we could write out the null and alternative hypotheses in words and in notation. The null, as we said before, is usually a statement of equality. So in this case, the null is that the slope is equal to 0. The alternative is that the slope is not equal to 0. Based on what we just talked about, then the null hypothesis in words is that there's no association between score and attractiveness. The alternative then is that there is an association. So take a second to go ahead and pause the video and think about which test we've done that's super similar to these hypotheses in words. Okay, so, so did you pause the video? This has reminded me of a meme that I will, if I remember, I will post a link to the meme in the description of this video that kind of relates to this. But these should look similar, at least the words part. This is similar to our chi-square test, right? Our chi-square test of association. The chi-square test was when we were looking at the association between two categorical predictors. This situation, we're looking at whether there's an association between two quantitative quantitative variables. So that's kind of the only difference between the two. Check, we've already talked about those conditions, and so we're not going to go over them again here. Calculate, we're going to just use our general format for our usual test statistic. And so we usually have this point estimate minus the null value divided by the standard error. And so now we're going to start to make use of some of the other stuff in this table that we skipped over. So in this table of output, let's go ahead and just be very clear about what each of these columns mean. We already talked about the estimates. That's just the estimate for the intercept, estimate for the slope. This standard error obviously kind of stands for standard error, so that one's pretty simple. The t-value column has a couple of test statistics. And these are for testing. The first one is for testing whether the intercept is 0. The second one is testing whether the slope is equal to 0. And then finally, this kind of weird one is R and some other software's notation for a p-value. And so those two p-values up here, again, are for testing the first one is for testing the null that the intercept is 0. The second one is for testing whether the slope is 0. So the standard error previously has been something that we've had to just do a brief calculation for by hand. And the standard error for the slope is this kind of mess. So that's our formula for the standard error for the slope. And so this, man, I'm full of memes today. This makes me think of another meme, the one of Randy Jackson from American Idol saying, "That's going to be a no from me, dog." So that's going to be a no from me, dog. Like, I don't want to calculate that, and you shouldn't want to calculate that either. And so we're always just going to grab the standard error from the table. We're not going to do this kind of by hand terrible calculation. So I'll just write hard pass. All right, and so once we're kind of here, the rest of the steps should look similar. We're gonna talk about calculating the t-stat and the p-value, though again, you could just grab them from the table. And so our degrees of freedom for this t-stat are 461, because remember from page 9 had our sample size of 463 courses. These degrees of freedom kind of just pop out of nowhere, but we're subtracting 2 now instead of subtracting 1 because there are 2 regression parameters. So the 2, we have a slope and an intercept. Okay, and so we could again now figure out what the t-stat is based on that kind of formula that we had before of our point estimate minus the null value divided by the standard error. Since we're talking about the slope, I'm looking in this second row only, and I'm kind of just ignoring this first row because we're not doing a test about the intercept. And so our t-stat is going to be 0.06664 minus 0 divided by 0.01629. If you do that calculation, you should wind up with 4.09, which matches the t-stat that the table of output gives us. So that should make sense. We could draw our null distribution. So this is a t-distribution centered at 0. We could mark our observed t-stat, which is somewhere over here, and then shade the tails to represent the p-value. If you go to stat key to get that p-value, you should wind up with something like that. And so let's check to make sure that that also matches with our table of output. And so it does. And so for anyone who kind of needs a quick refresher on this scientific notation that software programs end up using, this 5.083e minus 0.5, what that means is that you're moving this decimal place to the left 5 spots. And so this p-value is going to end up being very, very tiny. So it's going to be that. So these two are the same thing. It might be worth it to kind of become familiar with this type of notation since it's what most software ends up doing. All right, and so we're going to skip over this confidence interval stuff for the next video and just jump straight down into our conclusion. And so again, for our conclusion, we want an interpretation of our point estimate first. So remember, our point estimate was the fitted slope, 0.06664. And so I'm going to say, okay, we've already done this interpretation. So for a 1-point increase in attractiveness, we expect the average course evaluation score to increase by 0.06664 points. All right, so that is our usual first statement about a point estimate, and now I just want a statement about how much evidence for the alternative hypothesis. And so since our p-value is super, super tiny, then I would say, okay, there's strong or convincing evidence. And then I just want to state what the alternative hypothesis is in context of the problem, so that there is an association between professor attractiveness and course evaluation score. Give our t-stat, and then give our p-value. Okay, and so I'm not sure how surprised or if you're surprised at all by this result that we did end up finding strong evidence for an association between attractiveness of the professor and their course evaluation scores. I was at least a little surprised when I first looked at this data, but it's kind of an interesting study to look at, and we'll, in the next section, we'll get into looking at differences across gender. And so I'm sorry this video is long. I told myself never more than 10 minutes, but it just didn't really make sense to break this one up at any point. And so, as always, let me know if you have any questions.